Hi, this is Dr. Poonam Upadhyay, Professor in Department of Electrical and Electronics Engineering in VNR JYOTHI Institute of Engineering and Technology. Continuation to my last lecture where I discussed the behavior of elements, inductor, capacitor under transient conditions. So I'll continue my lecture by considering this behavior under the DC transient response. So analysis of DC transient is the continuation of that, where we'll be taking RL circuit and we'll try to understand how it behaves when excitation is applied to it. So let me take the circuit with DC excitation. Now, at t equal to 0, when this switch is applied, when t equal to 0, this switch is applied. So by KVL, this KVL leads us to the differential equation, first order differential equation, as voltage across this resistance is I into R plus across the inductance is L di by dt. So we get a first order differential equation. This first order differential equation will give us the understanding how much is the transient current in the circuit. So let us solve this first order differential equation by bringing it in the form of equation di by dt plus R by L into I equal to V by L. To find the solution of this, there are a number of methods to find the solution of first order differential equation. The simplest method is multiply the constant which is coming as ratio of R by L, exponential of this constant, multiply both sides, like e to the power R by L into t di by dt plus R by L I e to the power R by L into t is equal to V by L e to the power R by L into t. So we see here it is like differentiation byproduct. So we can bring into the simplest form as d by dt I e to the power R by L into t is equal to V by L e to the power R by L into t. Now, this will give us, after integration, as I e to the power R by L into t is equal to, integrating this one, integrating V by L e to the power R by L into t dt plus constant of integration. So when you integrate this, e to the power I into e to the power R by L into t is equal to V by L e to the power R by L into t divided by R by L plus k. So this will give us I. When you bring this exponential to the, divide this complete expression by this exponential term, you will get V by R plus k e to the power minus R by L into t. So we see this complete expression. We have one constant term as V by R and another term which is the exponential decay with respect to time. This part gives us for current as forced response, and the response, the term which is having the time value, exponential decay value, this gives us the transient response. Now let us try to find out what is the value of this constant K. So for that, what we'll do, we'll analyze the circuit at t equal to 0 when switch is closed. So at t equal to 0, as we know that inductor behaves like open circuit. This is when switch is applied, switch is closed. We have resistance here and inductor will give us open circuit. So you see current at under I0, you find that I0 is 0. That means at t equal to 0, our current is 0. So this condition we will use in this differential equation. Let me give this as number 1. So when you substitute this, you get here 0 equal to V by R plus K. So this gives me value of K as minus V by R. So this expression, I find the expression for current as I equal to V by R minus V by R e to the power minus R by L into T. I can simplify this as current is my function of time because I am having here exponential term. So I get here V by R 1 minus e to the power minus R by L into T. Now if I plot this characteristic with respect to time, I find here that current is reaching to peak value V by R. This is time and this is my current response I. So when I plot this, this is my peak value as V by R. So current shows the nature exponentially increasing and reaching to the steady state like this. This is my response of I of t. Now, question comes here, how fast it reaches to the peak value or how slow it reaches to the peak value. For that, we need to find out what is the time constant of the circuit. So time constant is defined as time at which exponential becomes unity. This is my current expression. Exponential become unity, that means my minus R by L, or I take here plus sign, minus is not required here because we are talking about the time. R by L into T is equal to 1. When my exponential is becoming 1. Minus sign we will be using here. So this gives me time is equal to L by R, which we call it as time constant. It is called as time constant. For RL circuit, time constant is L by R. Now, when my exponential is minus 1, I have here V by R 1 minus e to the power minus 1. When I substitute the exponential value here, I get I of t is equal to 0.632 V by R. If I take exponential minus 1, that is somewhere 36%. When you subtract that, you get here 63.2% of peak value. That means time constant is defined here as time at which current response reaches to 63.2% of the peak value. This is 63.2% of the peak value. Here, this is my time constant, tau. And here I have 0.632 V by R. Okay. Now, if you take the time t equal to 2 tau, My current will have I of t will be 1 minus e to the power minus 2, and it will be multiplied by V by R. This comes close to 85% of V by R. If I take t equal to 3 tau, my current comes 1 minus e to the power minus 3 V by R. I get close to 95% of V by R. So as I increase the time constant, as I increase the multipliers with the time constant, I slowly reach to 90% and then 100% of V by R. Okay, so time constant is the time which decides how fast current or voltage response reaches to its final value. So for this RL circuit, time constant is L by R. With this, after finding my current response, I can find what is the voltage across this resistance, that is VR, and what is the voltage across this inductance, VL, like this. So my VR is I into R. I have here V by R 1 minus e to the power. Now I can write minus t by tau. And R multiply with R, it is R. R gets cancelled. I get the voltage across the resistance as same nature as the current has. Voltage across the inductance is VL equal to L di by dt. When you integrate this, you get V e to the power minus t by tau. So when you plot this, you see here, this is time, this is voltage response. You see that resistance, voltage across resistance is following as we have the current, like this, same nature. And inductance is decreasing from the peak value. So inductor is decreasing from the peak value. This is my VL, this is my VR. So it is reaching to the peak value as capital, decreasing from the peak value and going to the 0. That means the voltage across inductor is leading towards 0. When voltage across inductor is leading towards 0, that means this inductor at the final stage, it will behave like a short circuit. Voltage is going to 0, so inductor will behave like a short circuit. When it is at t equal to infinity. At t equal to infinity, inductor will behave like a short circuit. Now, let's come to C power. We got I as V by R 1 minus e to the power minus t by tau. We got voltage across resistance as V 1 minus e to the power minus t by tau. We got voltage across inductance as V e to the power minus t by tau. Now let's understand what is the power here. Instantaneous power. So when you take the power across resistance, it is VR into I. That means it is V square by R 1 minus e to the power minus t by tau, and 1 minus e to the power minus t by tau. That means I am having here v square by r, 1 minus e to the power minus t by tau ka whole square. And voltage across inductance is VL into I. That also when you multiply this, you get V square by R e to the power minus t by tau minus e to the power minus 2t by tau. This is my inductance power. My total power will be sum of these two power PR plus PL. So I get here, when I sum both the power, I can expand this as V square by R, 1 minus 2 times of e to the power minus t by tau plus e to the power minus 2t by tau. So if I sum them up, I get here V square by R, 1 minus e to the power minus t by tau plus e to the power minus 2t by tau. This I get here. So if I plot this power, I see the resistance power is same like total power. So if I plot resistance power and inductance power and total power on the plane with respect to time, so I get here this is the total power I am having, that is V square by R. So my total power nature is exponential in this, like this. This is my total power, PT. And my resistance power is also similar nature somewhere and reaching to total power. This is my PR. But when you look at the inductance power, it doesn't have any initial value as well as final value. So when you plot this power, you will see here initial power is 0. It has some power, then it will go to 0. This is my inductor power, PL. So inductor power between 0 and some value, while going towards 0, the final value, it is reaching to 0. You can see between this initial and final value, this accounts for energy storage. So that's how inductor stores energy. So you can see here between 0 and final value, the inductor has some power and then it is going to 0. So that's how inductor behaves under transient condition, and depending upon the self-inductance value and the type of material, it responds, the stored energy responds back to the operations, to the switching operations, to the fault conditions, to the various operation of the circuit. So that's all for analysis of DC transient for RL circuit. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.